This video is entitled Attributes and goes along with Chapter 4 of the book Introduction to Database Systems Modeling and Administration. I'm Dr. Reneau from Shawnee State University, and I'll be taking you through this video presentation. In a previous video, we described an entity as something, an activity or a thing or a person or something within a data model. Attributes are the properties of those entities. Um, Actual values, they're the names of the types of values that make each of these entities uniquely different. An attribute is usually given a name, and we'll sometimes call that a column name if we're talking about a specific database. An attribute should also be atomic. And when I say atomic, an attribute should be a single value. For instance, a person's name could be a single value, but do we want to split last name, first name, middle name, surname or honorific that goes before or other designations that go after a name into different columns, into different attributes? And I think for a name the answer is yes, but for like a street address, do I need to split the number in the house, the house number and the street name apart from each other? Probably not, because an address is atomic. Um, so we want the attributes each to contain a single, unique, identifiable kind of value, and then each of these attributes will have a specific domain. And a domain means a valid range of values. For instance, um, a domain for birthday. We can't have a customer who was born before a customer today who was born before 1900. I mean, they just can't be that old. We can't have a customer today that was born someday in the future, on a different day in the future. So we could easily say that a birthday, for instance, for a current customer would have a domain of 1900 to today's date, and it has to be a date in a specific format of year, month, day, maybe, or however we define it. But we can define a rule that goes along with each of the attributes, and we call that rule that defines the valid range, we call that the domain of an attribute. Attributes come from two different origins. There are attributes that come from the natural world. We call those natural attributes, and attributes that we as data modelers, designers, database people, computer people make up, and we call those synthetic attributes. A natural attribute is a inherent property of whatever the entity happens to be. And usually an entity will know these things about itself. For instance, a name, a description, an address, a location, a weight, a size, a color, all of those kind of natural things that go along with an attribute. A person would have a natural attribute of language spoken, birthday, name, address, uh, country of country they were born in, all kinds of these natural attributes that an entity would know about itself. If an entity knew anything about itself, an order would have natural attributes like order date, ship date, what customer placed the order, what was the order total, how much tax was collected on the order, those kinds of things. The maybe tracking number or numbers associated with an order. So those are all attributes that go along with a natural entity, natural attributes that go along with an entity. Synthetic attributes we usually add to give meaning, or we add for the database itself. Broad categories are sequentially assigned numbers. For instance, let's go back to placing an order with an order entry system. Every time we get a new order, we just add one. Next order, next order, next order. Makes sense. That's a synthetic attribute. It doesn't really matter. The order could be anything, any number it wanted to be, but we just assign the next available number. There's also a random sequence that could be assigned. We call it a UUID, or a universally uniquely identifier, or abbreviations. A UUID you might have seen is a great big long string of letters and numbers with dashes that you'll sometimes see well, you'll sometimes see it on a website or in a URL or something like that. And abbreviations are also synthetic attributes. The entity might not know that abbreviation about itself. I said in the introductory slide that attributes need named. We each like name and address and city, state, zip, if or postal code, if you want a more generic than just a U.S. name for a postal number or postal code. Um, there's no standard for naming attributes. There really is no specific standard, but your institution or employer may have a specific standard for how they want you to name them. Do they want them singular, plural? Do they want them in upper and lower case? Do they want them containing spaces or not containing spaces? Can an attribute name contain special characters or not? My personal standard is that attribute name should be either in camel case or snake case. But let's go through the cases. There are four general ways that most people will write an attribute's name. Pascal case, where the first letter of each word is capitalized and the word is jammed together without spaces. So last name would be capital LAST, capital NAME. Pascal case. Camel case is similar to Pascal case, except the first letter of the second and subsequent words are capitalized. So it's the same as Pascal, except the first letter is lower. And it's got humps of uppercase letters where each word breaks like a camel's back with its humps on the back of the camel. Snake case, everything is lowercase. All the words last underscore name, and we use underscores uh, to separate words. Spaces can be problematic when we get into actual writing of queries for real databases. So it's, I think, best if we just start our attribute naming with the notation or the nomenclature or the style that we're going to use when we actually go build a database. So, and again, spaces in a attribute name are very problematic. Special characters in a attribute name can also be problematic. So, A through Z, the numbers 0 through 9, and maybe an underscore, and anything else, just don't do it. Lowercase, an attribute could be all lowercase, and it can be multiple words all jammed together, lowercase, but those start to get to be difficult to read if you've got a long attribute name. So, naming of an attribute can be anything you want it to be, but make the name meaningful. Don't call the attribute stuff or crap or something uber generic that would not describe what the column what the attribute contains, because again, we're trying to create a model so that we have understanding. And if you don't use meaningful attribute names that really describe what's in that attribute, then your model's going to not have the information it really needs to have. This is a list of recommendations that I went over most of those in the last slide. Again, just be consistent. Inconsistency will cause errors and slow development. Names should contain only letters, numbers, and underscores. Choose a style, use it. Make sure your abbreviations are consistent and that names are all either singular or plural. Customer, customers, order, orders, item, items, that kind of thing. Just be consistent. That's the most important part in any model. In the introductory slide, I said that attributes have a domain or a valid range of values. When we're defining the domain of an attribute, we look at the business rules or the business needs or the needs of our clients to figure out what the valid range of those are. In most modern databases, though, they're going to be stored in these general types of data that are built into, or domains of data into the database. And those are fixed precision numbers, floating point numbers, strings, Boolean values, datetime values, and binary objects. A fixed precision number is a number that has a defined precision. I mean, it just kind of makes sense by its name, but that means the number of valid digits in a number, or the valid range from high to low, we know, and it cannot exceed that. A fixed precision number can be an integer or a decimal number, but if it's a decimal number, we've also fixed and defined how many digits beyond the decimal point, how many fractional digits we will allow or not allow. So fixed precision numbers are usually stored in a database system as either a 16, 32, or 64-bit number. A 16-bit number can contain the values from positive to negative 32,000. A 32-bit number in a range of positive to negative 2 billion, and a 64-bit number, well, it's huge. Um, and then when we're again defining a fixed precision decimal number, we would say, well, it has 8 digits of precision on the whole number side and 3 digits on the decimal side, and the number will be stored in such a way that it will always have that pattern or that size, and its precision is fixed in the definition of the attribute. A floating point number will have a variable number of digits of precision both on both sides of the decimal point, and is stored as an approximate value in the database system. Um, but it's stored as an exponent with a yeah, it's stored as an exponent, so there can only be so many digits of precision in that exponent, but it can go from very large to very high magnitudes with a limited precision. This is often used for a continual reading, like maybe a seismographic measure, or a measure a measure of a temperature, or measure of something that can have a very large range. Um, a lot of database people don't use a lot of floating point numbers because we like to know exactly what we're storing and the specific range. But again, for scientific data, you will often need to store floating point values to be able to cover the full range of possible values. A string is a sequence of letters, numbers, and other symbols, characters from the keyboard, Unicode characters, special characters, all of that, um, and are used to represent things like names, addresses, descriptions, text, those kinds of stuff. Um, in the SQL language that we'll be introducing later in this semester, in this book, you'll see that strings are surrounded in single quotes, a single quote with a string and a closed single quote. And strings can be variable length or they can be fixed length. A string might be required to be a four-letter code that we've defined in is that attribute. That attribute has a range of a four-letter code, or it could be a variable length from zero length to even several thousand characters long. When we define a string's an attribute as a string, we probably should also define its maximum storage length or define if it has that fixed length as I was describing. Boolean values. There was a mathematician many years ago named George Boole who studied the algebras of true and false. Kind of interesting, actually. You would think that algebra with only two values would be simple, but it's pretty complex stuff. And so a Boolean value is a true or false value. It may be stored as its own type, or we may store it as an integer, either 1 or 0 or negative 1 for true and false. Let's think about an attribute that might be Boolean. Maybe we've got a database of people or a database table. We've got an entity of people in our data that we're modeling. Maybe we want to know if they're alive or dead. Dead, alive. True, false. They're not alive. Um, maybe they're maybe they're in good standing with us. True, false. Um, maybe we just don't have the number of their offspring, but maybe we want to know and want to track, do they have children or not? Um, true, false kind of values. Uh, but it's kind of, yeah. Another common attribute domain would be date and time. In a database, relational database system that we'll again get later in the book, you'll see that there's a column type called, or an attribute type called date time. And a date time is a way for us to store a date, a time, and a time zone in a single attribute. So when I'm storing dates or when I'm thinking about dates, I just put them in a date time because that gives all the information I possibly need. Because if I just store the year and the time, if I'm an international organization, is that the time in London or is that the time in Tokyo or is that the time in New York? So we really do need to store all of that information about a specific date or time. And by storing it in a date time, it makes it really, really easy. Date times could be used for dates only or times only, or there probably is a date and time attribute type that we can use or domain. Also, remember that domains have specific legitimate, correct values. So we can put a specific date range a date time as well by saying, well, we can't have a new customer who was born before 1900. Nobody's that old. We so we could say that a new customer's birthday has to be after 1900 and before today because we can't have a customer that's been born in the future. So again, we can also define ranges of specific values in addition to giving it this type. Attributes may also be binary objects, and you'll sometimes see them referred to as blobs. And blob is an acronym for binary large object. BLOB. They're used to store sound, video, encrypted strings, or other binary data. So if we wanted to include a picture of of a person or pictures of an item in our inventory, we could include those as attributes, as blobs. We could even include the biometric information about my thumbprint to use as to use in our validation of an employee when he logs in, or lots of other things. So a binary large object is for that unstructured data, that really unstructured data that we want to include and store into our database for quick access. There is a type of value that wasn't on my original slide of types of values or domains, but there is a special domain called null, and the null domain represents the value that there is no value. What? Let's just say that again. Null represents the value that the value is not known. It represents the not known value. It means nothingness. And that's kind of cool. But attributes can be null or not. For instance, um, someone's name. Could we have a customer with no name? Well, we probably would say no, they have to have a name. So we would define that attribute with a range of not null because they can't have no name. Could we have a customer who won't give us their address? Well, yeah, I guess we could. Um, that might be a business rule that we have to have an address for every customer, but I guess a customer could not give us an address. So the address field might be nullable. We might be able to store the value of nothingness or the value of unknown for an address. This video and the next couple of chapters are going to start moving us into creating the LDM, or the logical data model. The shape for the entity in a logical data model changes a little bit, changes to be a rectangle with either rounded or square edges divided into two sections. The top section will include the name of the entity, and the bottom sections will include a list of the attributes. You can see here the attributes are in um, uh, snake case. Yeah, I had to think there for a second. And here in our owner entity of an owner, we're tracking their owner ID number, which would be a synthetic attribute because the owner doesn't know. Do you know your customer number at all the stores and all the places you go? No, but you probably have one. They do know, though, their last name, first name, phone number, and email. And you can see that each of those are nice atomic chunks of data. Um, so that's the entity shape, and this is the entity shape used in something called crow's foot entity relationship diagramming, ER, also called ERDs, and that's the type of diagramming that I've seen used in industry most, and it's the type of diagramming we'll be using in this book for our more complex data models. Here's a second example. Here's a second example of an entity relationship diagram that includes domain types, includes the type of the domain along with the attribute. This includes our video for Chapter 4, Attributes. I'd like to say thank you for watching. Thank you yeah, thanks for watching, and I'll see you in a future video, I hope.